Okay. Okay, so let me remind you what we did last time. So I think at some point we wrote so these relations, which are the equation of state for both for bosons, KBT, and this is equal to G half of Z, and the other one, which is lambda cube n equal to G 3R of Z, where Z is the fugacity, and this function here, they are called Bose function, and GK of Z is a series which is done in the following way: d to the power of L, and here you have L to the power of K, L to the power of K, and here L runs from 1 plus infinity. Okay. So this is the relation basically that provides the equation of state, which means the pressure as function of the other variables, whereas this one is the equation that provides me the link between the density, temperature, and fugacity. Of course, here this equation is an implicit equation that I cannot solve analytically, because the temperature appears here, the lambda, and also the Z, basically in this data, okay, through this complicated function, which is this Bose function. And I think that last time what we saw was the classical limit of these quantities, and actually the first correction. Let me just repeat this argument. So the classical limit, so now, okay, first of all, Z is a number between 0 and 1 for bosons, and the classical limit is the one that I get, classical limit, when Z is small, okay, close to 0. And indeed, in the classical limit, for instance, I can keep the first order in this function here, and I see that lambda cube n is equal to Z, but Z is equal to E beta mu. And of course, this is just the equation for the chemical potential that we saw, I think, in the microcanonical ensemble. No? So this provides me that mu is KBT logarithm of n lambda cube. Okay, and you see also that on the others that Z approaches 0, which also means that lambda cube n is a small number, which is small density or large temperature, or large temperature. And well, similarly, I can get from the previous one, and this we did last time. So then one can include the corrections in second order in Z, and for last time, let me just repeat this formula that last time we were running a little bit, that P lambda cubed divided by KBT is equal to Z at the first order, which is lambda cubed n. Notice that if I stop here, I get just the standard ideal gas equation of state, which is P equal to density times KBT. And then there was a correction that was the following. So it's lambda cube n squared divided by 2 to the power of 5/2. And this provides me the correction due to the quantum nature of those particles, as due to the fact that they are bosons and the wave function is symmetric. Okay. We will get just the opposite in the case of fermions, because fermions do not like to overlap, and therefore we will have an effective repulsion, whereas here we have sort of effective attraction for the case of bosons. Okay. Okay, so this is the classical limit, first of all, and the first order correction to the classical limits that appears here. Okay. Now we will do the opposite. We will go in the other direction, which means z approaching 1 from the left, and which is the quantum behavior now of the Bose-Einstein gas. And we will see that something weird will appear, which is the Bose-Einstein condensation that we are going to explain today. Okay. So next topic is Bose-Einstein condensation. That I'm pretty sure that you haven't seen in the past, I guess, but correct me if I'm wrong. Okay. Usually with the Bose-Einstein distribution or the Bose-Einstein statistics, most probably you have seen the black body for sure, and the Debye model for the phonons, maybe the solids, maybe. Yes. Okay. The Einstein model, we saw the Einstein model, but in structure of matter, maybe you have seen the Debye model. Okay, so Bose-Einstein condensation. So the starting point is this equation here, but now from the previous equations, I was forgetting completely about the fact that there is a divergence, which is related to the situation in which the particles have zero momentum and z approaches 1 from the left. Okay, but now let me introduce back again that specific correction, in particular in the density equation, that was the following. Lambda cube n is equal to g3 half of z. Now here, if we are approaching z if we are considering z approaching 1, we have to introduce the correction, which was lambda cube divided by the volume, and here we have z1 minus z. Okay, this was derived when we saw how to write down the equations for the Bose-Einstein gas. Okay, where this quantity here, v1 minus z is equal to n0, is interpreted as the number of particles occupying the state with k equal to 0. Okay. Now, first of all, let me make a plot of this quantity here, because this is the starting point. So let's make a plot of this function. So this g3 alpha of z as a function of z. And z is a variable that I was reminding you before, that is must vary in the interval 0 to 1 because of this relation, because it's a number of particles, a positive number. And now let's make a plot of this quantity. When z is close to 0, we see that the leading term is linear in z, so therefore this is close to 0 at z. And so it will be like something like this. And for z equal to 1, which is the maximum value that this variable can have, we see that the behavior of this function is the following. It reaches a maximum, and the maximum is located at this point, is equal to 2.612. is the maximum. And the derivative at the maximum is divergent. So G prime 3 alpha 1 goes to infinity. Okay, or better to say, for Z approaches 1 from the left. And this can be easily seen by considering the fact that there is a relation. Well, we can also try to compute it directly. So G3 alpha of Z will be the sum of Z to the power of L and L to the power of 3 alpha. And here you have L from 1 to plus infinity. So if I compute the first derivative of this function, questo era 3/2, no? Sì. The first derivative of this function, yeah, so I get 3/2 minus 1, which is 1/2, no? So first derivative of 3 is equal to sum from L1 plus infinity of Z to L minus 1, then I get a factor of L here, and therefore I have 3/2 minus 1, which is L to the power of 1/2. Okay? And this is divergent when Z is equal to 1, no? Because will be 1 divided by L to the, no, square root of L does not converge this series. Okay, good. So this is just, well, this is not very important for our discussion. What is important is instead that this function here is limited. It has a maximum. This is very important for the reasons that you will see in a moment. So let me do this. Tra l'altro non ho chiesto, ma la casa si vede? Sì, no? Sembra di sì.
Sì.
Ok, grazie. Okay, so let's write again the equation, the starting point. But let me switch from the left-hand side to the right-hand side. In particular, let me consider here there was a volume, lambda cube n 0 divided by the volume is equal to lambda cubed n minus G3 alpha of Z. Okay, now this number here must be positive because it's a number of particles divided by volume and the lambda. Okay, of course this is positive and this is positive. And also G3 alpha is limited. So this equation, okay, so these are always positive. For a certain value of Z, so for Z strictly less than 1, this equation provides me the way to compute the relation between the density and the fugacity, and also I have well, a quantity here which corresponds to the occupation of the ground state, which actually will be 0 for a reason that I'm going to explain in a moment. But what happens, well, it's an infinitesimal quantity as it should be. But what happens when Z is equal to 1? Now, when Z is equal to 1, of course, here this is limited. If you want, this contribution is so this term corresponds to the ways of arranging the particles in the continuum of the levels. Whereas this factor here corresponds to the occupation of the ground state. Okay. Now, here this is important, n number of particles conserved. If the number of particles is conserved, then somehow you have to arrange this number of particles between the continuum and the ground state. Okay, so in a normal situation, when z is less than 1, as we will see in a moment, what happens is that I distribute the particles in the continuum, and all the levels of the continuum, including also the ground state, have actually an infinitesimal occupation number, because this is a continuum. What happens is that when z is equal to 1, when z is equal to 1, this has a maximum, and therefore, by fixing the density and the temperature, the only way in which I can satisfy this equation is to increase the number of n0, which is the number of particles in the ground state. Okay, so suppose that z is exactly equal to 1, and lambda cubed n is a large number. How large? Well, larger than, or strictly larger than G3 alpha 1, which is a fixed number, which is 2.6. So now in this case, if this number is larger than this, okay, maybe I don't know, it's twice this number, the only way in which I can satisfy this equation is to have a finite occupation of the ground state. Okay, a finite number of particles in the ground state. Okay, in this situation, and zero must be finite. This corresponds to a macroscopic occupation of one single level. Okay. And as I said before, this situation occurs when, in the cases in which z approaches 1 or is equal to 1, and this number here is larger than this. Okay, because in that case, n0 must be a finite number. Why this situation is strange, is weird? Because usually it's not like that. Usually, if I take the continuum, notice this. In the continuum, the occupation of a certain level is provided by the Bose-Einstein statistics time a differential, no? So in the integral, I have an integral over dq of q squared, and here I have the epsilon q beta minus beta, and then it's minus 1. So in the continuum, the occupation of a certain level or a certain state characterized by a wave number q is provided by this function here. So it's a differential. It's a differential. Well, it's an infinitesimal occupation number, no? Because if I have a continuum and I distribute the particles in the continuum, of course, for a single specific state, the number of particles will be infinitesimal. Is it okay? So usually it's like that in the continuum, but here instead I have the n0 instead is finite. Okay, and this is the core, if you want, of the Bose-Einstein condensation that occurs when z is approaching 1, or is equal to 1, and this number here is larger than a certain threshold, that is this 2.6, which is the value of this function at z equal to 1. Okay, so in that case, I have that n0 is a finite number, therefore I have a macroscopic occupation of one single level, What is instead forbidden in the continuum because the occupation number is proportional to this quantity, which is clearly an infinitesimal quantity. Okay? Now we will see in a moment which are the conclusions, well, which are the consequences of this observation. But let me repeat again. So the situation here is the following: when z is equal to 1, this is the maximum, and therefore, if this number is fixed, the only way to satisfy this equation is that n0 is finite. Okay. Now, the critical situation occurs when this c is equal to 1, and that lambda cubed n is equal to this function here. Okay, so if you want, n0 starts to be finite. Finite, but not not finite, not infinitesimal means when lambda cubed n is equal to this function here, computed at 1. Okay, so this is the threshold, if you want, condition for BC, which is the condition for obtaining a finite value of n0. Ok? Questo mi sa che lo devo buttare. Now we can make a plot. Let me call this lambda cubed n. Let me put a c here equal to G3 alpha 1, where this C stands from critical. Okay, this is the critical condition for having the Bose-Einstein condensation. And let's make a plot. The first diagram that I want to make is the NT diagram. So if I plot here n versus t, considering the lambda scales as 1 over square root of t, here you have a lambda to the power of, t to the power of -3/2. And therefore, if I plot the density as a function of temperature, this is a number, I get a function like this, where this is n proportional to t to the power of 3/2. Okay? So this is the plot of basically this function here. Okay? Now, here there is the BC, because in this region, what happens is that well, this function here, so this number lambda cubed n is larger than this, whereas here this is the normal phase. Okay, whereas here is there is the Bose-Einstein condensation region, and the critical line is provided by this function here. Okay? I can also find the critical temperature at fixed density. Well, it depends on what I fix. I can fix the temperature here and find the critical density, or I can fix the density and provide the critical temperature. No? So let me find the critical temperature for a fixed value of n. I can define a critical critical temperature by using this relation. So lambda cubed is what is h to the power of 3. Then I have 2 pi n kBTC to the power of 3 half times n equal to g3 half of 1. From which I can get the KBTC, the critical temperature, is equal to, well, h cubed n divided, so h cubed n divided by this g3 alpha 1 is to the power of 2/3 and 1 over 2 pi and 1. Okay. And of course, similarly, I can find the critical density from here if I have, if I fix the temperature and having the critical density, I can read it just from here. It's just this number divided by the lambda. Okay. Whereas the critical temperature is provided by this function here. Okay. Just a short reminder of what we are doing by considering the fugacity. When considering the fugacity, V was equal to E to the mu beta, and therefore since Z is approaching 1 goes in the BC, from the left, what happens to the chemical potential? The chemical potential must go to 0. Okay. From the left. Okay. Okay. We saw last time that the chemical potential of the particles is negative in the case of bosons, because Z is restricted to vary between 0 and 1. And therefore, when Z approaches 1 from the left, which is the quantum situation, the purely quantum behavior, as opposite to the Z equal to 0, which is classical behavior, the chemical potential approaches 0 from the left. Okay. Now we can try to study a little bit more in detail what is this BC, what is how is this new phase characterized. What the first thing that we can do is to find the number of particles at a certain value of the temperature, for instance, that are in the Bose-Einstein condensate, and the number of particles that are in the continuous loop. This is the first thing that we can do. The starting point is the equation that we derived before, well, that we wrote at the beginning, which is the following. This 3 half of Z, and here you have lambda cubed divided by the volume, and here I have this N0. Dunque, vediamo cosa mi conviene fare. Where N0 is Z1 minus Z. Okay, let me multiply by the volume. So here you will have lambda cubed N, and here you have a volume V3 half of Z plus lambda cubed N 0. Okay. And also let me divide by the lambda cubed. So here I have a lambda cubed here. You can remove this. And from here, what I get is that n0 is equal to n minus this quantity, so minus b lambda cubed, okay, which half of c. Now let me multiply, well, divided by n, 0 divided by n, so here n, and here I get 1 minus dunque, a moment. Okay, so here if I want to compute the condensed phase, I should put z equal to 1, of course. So let me do this before. So of course, if I am at the normal value of z, so far from 1, this will be 0, because it will be infinitesimal actually. So let me put first z equal to 1 for the BPC condition, and therefore here get that n is equal to b divided by lambda cubed now for 1 plus n0. Otherwise, if z is not close to 1, this number will be 0, will be an infinitesimal quantity. Okay, so let me continue from the point I was before. So now n0 is equal to, divided by n, is equal to 1 minus what I was doing before. So I have the volume divided by n, which is 1 over the density. So this G3 alpha 1, and here I have n lambda cubed. Quindi n0 diviso n uguale a 1 meno G3 alfa. Ok. Okay. So now let me write here the fact that if I do n lambda cubed critical, this is equal to G3 alpha or 1, whereas n lambda cubed not critical, so normal situation is equivalent of this. And in both cases, at fixed density, lambda scales as, so the lambda cube, so this function here scales as t to the power of minus 3 alpha. Okay. So basically, by considering these two equations, the coefficient will be the same, but they are proportional, this to the Tc to the minus 3 half, and this to Tc to the minus 3 alpha, okay, which is equal to 1 minus T divided by Tc to the power of 3 half. Okay. So let me repeat what I'm doing here. So from this equation, I see that G3 half of Z scales as T to the minus 3 half. And also n to the lambda 3, of course, scale to the power of minus 3 half. Whereas from here, I see that G3 alpha 1 scales as Tc to the minus 3. Okay. And the coefficients are the same since I'm computing ratios between the same function basically, but one is computed at 1 and the other one is computed at C, general C. Okay? Therefore, I get the ratio between temperature and critical temperature. Okay, so I can make a plot now. questo è il cancellino. Per make the plot of this quantity, here I will put n0 divided by n. Now for t equal to 0, this is equal to 1. And for t equal to tc is equal to 0. Therefore, I will have a curve the temperature and is the condition t equal to tc. Okay, so I see from here that if t is equal to 0, so really equal to the 0 absolute value of temperature, all the particles are in the ground state. Because in that case, n, which is the total number of particles, is equal to n0, which is the number of particles in the ground state. Okay. All the particles are in the ground state. Okay. When I vary the temperature between 0 and Tc, I will have a certain fraction of particles in the ground state. Anyway, a macroscopic number of particles. Okay, so for T larger than 0 and less than Tc, I have a macroscopic number of particles in the ground state, and the rest is in the continuum. And when I reach T equal to Tc, no particles in the ground state, so I distribute those particles in the continuum. Okay, that's it. Okay. So in here we'll have some particles in the condensate and in the continuum, but in the extreme situations, all the particles are in the condensate, or no particles are in the condensate, and they are in the continuum instead, distributed in the continuum. For this phenomenon to occur, it's important that the total number of particles is conserved. Okay. Actually, I will discuss the case of photons. Well, from standard textbook physics, there's no Bose-Einstein condensate for photons because they have zero chemical potential. So the number of photons is not conserved, and we cannot have BC. But actually, in the last period, something on this direction apparently occurred. Something new. Okay, good. Now let's start to see to characterize a little bit more the properties of the condensate. So here we saw how many particles are in the condensate as a function of the temperature. Now let's try to see which is the behavior for what concerns the equation of state when we are in presence of a Bose-Einstein condensate. So let's compute the equation of state. In particular, when in the situation in which T is equal to 0, everything is the Bose-Einstein condensate. T equal to Tc, no particles in the condensate. In the intermediate region, I have some particles which are in the condensate and some particles which are in the continuum. And of course, the properties, for instance, concerning the pressure, depends on how many particles are in the condensate and how many particles are in the continuum. Okay, and so let's see what happens. As before, let's write down first of all the equations for the Bose-Einstein condensate, for the Bose-Einstein gas, which are our starting point, where I'm considering now differently from what we did last time, the specific occupation of the ground state, because I'm considering a situation in which I can have a mixture of particles in the continuum and particles in the ground state, so in the common state. So this is the relation of n lambda cubed, and then I have a similar relation, p lambda cubed divided by kBt is equal to g 5/2 of z. Now, if we look at our notes, when we derived the equations for the Bose-Einstein, the equation for the boson gas, we had an additional term here, which is provided by the following formula. So minus lambda cubed divided by the volume, and here I have a log of 1 minus z. Okay? But now you have to consider, in principle, since I'm considering the possibility that z is equal to 1, and therefore I have these divergences. Okay? In the classical limit, we have neglected this term and this term. And now we are considering a situation in which we can have a BSC, a BEC, and therefore I need to keep the contribution of the ground state in both equations. Okay? But actually, this is formally correct, but actually in practice, this term will not contribute anything, and the reason being the following. So I see from here, in order this quantity to be finite, when z approaches 1, so this is a volume, and the volume usually is sent to the thermodynamical limit to infinity. Therefore, if I want this quantity to be finite, I have that 1 minus z must go to 0 as 1 over the volume. Okay. So in the thermodynamical limit, V is sent to infinity, and if I want the product, well, this goes to 1, okay? So it's finite, the number is finite. If I want V1 minus Z finite, and this must be finite because here, apart from the lambda and the volume, this is just the number of particles in the ground state, okay? So if I want this quantity to be finite, 1 minus Z must go to 0 when Z approaches 1 from the left as 1 over the volume. Okay, in order for this quantity to be finite, because this is going to infinity, this is going to 0, and in the BC, and if I want a finite quantity, okay, this 1 minus Z must go as 1 over the volume. Okay, and now you see the trick, because here, if this is true, when I consider this term here, in the thermodynamical limit, this is proportional to 1 over the volume times a log of 1 over z, which scales as the volume. And therefore is suppressed by 1 over the volume times the log of v. Okay, so this is actually 0 in the thermodynamical limit. Okay, so in conclusion, when considering the corrections to the density equation and the equation of state as due to the ground state, as due to the Bose-Einstein condensation, of course I have to keep this term, and I'm noticing that in order for this term to be finite, in the thermodynamical limit, 1 minus z must go to 0 as 1 over the volume, and therefore here we'll have a logarithmic divergence divided by the volume, and therefore this actually drops when the volume is sent to infinity. For this reason, when I will write the equation of state for the for the boson gas, I will just use this term here. Now, if we are in the condensate, Z is equal to 1, whereas if we are in the continuum, Z is different from 1. And in particular, one can also stress that the contribution, if you want, of the condensate, which will be this one, is subleading and therefore is vanishingly small in the thermodynamical limit. Said in other words, the particles that are in the ground state do not contribute to the pressure. And this is also intuitive in the sense that those particles are in the k=0 state, and therefore we do not expect those particles to contribute to the pressure because they are basically condensing in a momentum state with momentum equal to 0. Okay, so if you want, in other words, the particles that are in the condensate do not contribute to the pressure. Being at a state Q equal to 0. Okay. Good. Now, for this reason, when writing the pressure, because this is the function that I want to plot, I will just neglect this term because it's suppressed in the thermodynamical limit. So let me write again the equation before, after giving this motivation. Let me write again the equation. Suppose that we want to make a plot of the isotherms in situation in which we can have a BC. So let's work at fixed T. And let's consider this situation. So this equation: P lambda cubed divided by KBT is equal to G5 alpha of Z when n is smaller than the critical density. Okay, when n is smaller than nc. We make a plot of n and t again. We said before that here I have a critical line, and here we have the BC, and here we have the normal. Now suppose that we are fixing the temperature, so we are working along this line here, and suppose that we take a density smaller than the critical density. Okay, so we are in the normal phase. Okay? And therefore here I'm putting Z different from 1. Okay. Forse il calcolo poi lo faccio dopo di questo, anzi sicuramente lo farò dopo, calcolo pure le derivate. And this equation must be, of course, also integrated with the equation that n lambda cubed is equal to G 300 of Z. So if you want to, I fix the temperature, suppose that I fix the density, from this equation I find Z that I can put then here and compute the equation of state. Okay. What happens when n is larger than nc? So we are here now in the Bose-Einstein condensate. Now the P lambda cubed divided by KBT is equal to G 5 alpha of 1 in this case. Okay. Because this is the situation in which the critical density is large, the density is larger than the critical density, or we are in the BC. As you see from here, whereas So in the first equation, I will have that the pressure depends on temperature and density. So from here, the pressure P is a function of density and temperature, as usual. And dependence basically is in here, because as I said before, at a fixed n and temperature, I can compute Z, and then I put Z in here, and I will have therefore a dependence of the pressure from the temperature, which is also here, and the density. Whereas here, this is a number now. Lambda depends on the temperature. Here, I just have the temperature. So I see here that the pressure depends just on the temperature in the condensate. It's just a function of temperature, no dependence on density. Okay. Now, by observing these, I can make a plot. Actually, in this case, one can show that one recovers more or less, well, actually, when Z is equal to 0, the classical limit. So actually, in this case, those are almost normal isothermal curves of the standard behavior. Whereas this is a situation which is weird because the pressure depends just on the temperature. And if I'm plotting T6 isothermal curves, it means that I will have a plateau. So, facciamolo qua. Let me introduce the specific volume, 1 over m equal to V, called the specific volume. And if I consider critical density 1 over NC, I will get also critical specific volume VC. So what I want to plot now is a plot which is the standard plot in the PV diagram, but instead of making PV diagram, I will make a P specific volume diagram. Okay. And now let's compute, well, let's make a plot of two curves at two different values of the temperature. And the result will be something like this. Facciamo il disegnino, cerco di farlo bene. So here, where this number here is 1 over NC of T1. And these are isothermal curve with a certain temperature T1. And you see here that when the specific volume is larger than the critical specific volume, which is 1 over CNC of T1, I get like something like hyperbolic as in the classical gas. Whereas for V smaller than this quantity, which means density larger than the critical density, I get a plateau. The plateau is due to the fact that here the pressure depends only on the temperature and does not depend on the density. Okay? So here P is just a function of temperature. Okay? Not a function of or specific volume, which is the same. Now, if I make a plot with a larger temperature, I will get something like this. So this should be something like T2. Here I will have another point here, which will be 1 divided by NC of T2, where T2 is larger than T1. Okay, let me see if this is correct. If I have the NT plot, the line was going in this direction. So therefore, at larger temperatures, I will get a larger value of the critical density, and therefore a larger temperature will get a smaller value of the specific, the critical specific volume, no? Because if the density is larger, the specific volume is smaller. That's why here, this point here, this continuity point gets to smaller value, no? Because the behavior of anything is this one, okay? So if I take a larger temperature, the critical density will be larger, and the critical specific volume will be smaller. So the behavior will be like this. Unless at some point I reach T equal to Tc, and then when T is equal to Tc, I do not have a Bose-Einstein condensate anymore, and I will just have a branch like this one. Okay? Okay, so which are the notes that I want to make on this plot? And actually what we are going to compute, but forse devo fare una pausa prima, is that to some extent what I'm plotting here is very close to a first order phase transition. Because when I have a plateau in the pressure in the PV diagram at fixed temperature, what reminds me is the situation that we have analyzed for the van der Waals gas, for instance, in which I had P and B at a fixed temperature, and this plateau was corresponding to the mixed phase. And this feature is actually what happens when I have a first order phase transition. Okay, so actually, so this was for the van der Waals. Below the critical temperature, I had this plateau in the pressure that was interpreted as a mixed phase. So actually here this is very similar, but for the fact that I do not have this branch here, here it just goes to zero, but here, this region here, instead would correspond exactly to a mixed phase of normal phase plus BC. Okay. So what we are obtaining for the BC is something similar to a first order phase transition. And indeed, what we will see in a moment is that we can even compute the Clapeyron equation for this first order phase transition. And we will also see that there are some weird behaviors when computing the specific heat. Here we will find a discontinuity in the specific heat. Okay, so let me remove this. Now this is the PV plot. In which I can clearly see the presence of a sort of mixed phase. The other plot that we did was the following, was the NT plot. That was something like this, where here I have the BC normal. Okay. I'm making all the plots, the thermodynamics plot that characterize this phase. And another plot that we can do, and then we make a break, is the following. P versus temperature, which is the standard plot that we use, for instance, when plotting the phase diagram of water, for instance. We have usually a PT plot, and in this case, this PT plot is a little bit tricky for for the following reason. So first of all, let me notice that as before, so P lambda cubed is divided by KBT is equal to G 5 alpha of Z in the normal phase, whereas this G 5 alpha of 1 in the BC. And in particular, in the BC, this is a number. This lambda scales as T to the minus 3 half. Then I have another temperature here, so this will be T to the minus 5 half. Therefore, the pressure as a function of the temperature in the condensate, well, along the critical line will be something like this. So P scales as T to the power of 5 half. And actually, in this plot, the condensate is just this line here. Okay? It's just a line. So the points of this line corresponds to the condensate. Here, okay. This part of the diagram does not exist. Because when I fix the temperature, the pressure in the condensate is just one number. It does not depend on the density. So if I fix the temperature, I just have one value of the pressure. I cannot change the pressure as I want, okay? Because the pressure is just a function of the temperature in the condensate. That's why here I'm saying that this line here corresponds to the Bose-Einstein condensate point, whereas below this curve, here we'll have the normal phase. Okay. So it's a little bit different with respect to water, and indeed this phenomenon is quite interesting phenomenon, although treated in this way is a little bit artificial for some reasons that I will explain the following. But so let me make a final comments on these different plots. So here I have N versus T. I have a critical line here, which was derived by imposing that N lambda cube is equal to G3 half of 1. Here are the BC, here the normal. Here it is the PB plot with the isotherms, isothermal curves, and I see a mixed phase. Here, what we'll compare, if you want, with the plots of water, with the phase diagram of water. I have the PT plot, which the Bose-Einstein condensate states are just the ones occupied by the points along this line. Okay, this part does not exist, whereas here below this curve, that means when Z is less than 1, I have to use this equation here, and I will have the normal phase. Okay. And after that, maybe I'll stop for a while, and we will compute after the break. We will compute the Klepperian equation for this kind of first-order phase transition. Ok, facciamo una pausa. Okay. So just to make the comparison a little bit more clear, when I was plotting the phase diagram of water, well, we had something like this, no? This is the trouble point. This is the critical point. Here we have T versus T. This is the liquid gas. And we have computed here the shape of this line of first order separating the liquid and the gas by using, and then we derive the Clapeyron equation. And that was the following. Here you have the latent heat, which characterizes a particle that characterizes the first order phase transition. Then I have the temperature, and then here I have a difference between two specific volumes, which are the specific volumes of water and the specific volume of the liquid, so of liquid and gas. Okay, this was the Clapeyron equation, and this was the phase diagram. The phase diagram of water. So we will do the same, since we found something that reminds us indeed a first order phase transition. But now the plot is slightly different, because we said that here we have P versus T, and here we have a line that scales as P to the power of 5/2. Here we do not have anything here. Here we have the normal phase, and along these points we have the BC. Okay. So we are going to compute now the derivative of P with respect to temperature along the critical line. Which in this case would correspond basically, to this line here, for which N is equal to NC. Okay. Now the pressure in the BC is just a function of the temperature, and we said before is just I write the result directly. It's kBT divided by lambda cubed, and here you have a G 5R of R1. Okay. Now, if I want to compute the derivative of the pressure with respect to the temperature, it's better to single out this quantity here. So it's KB divided by H cubed. Here you have a 2 pi m KB to the power of 3/2. Power of 3/2. Then I have a temperature to the power of 3/2. It goes up and becomes 3/2 plus 1, which is 5/2. No? G. Mi sa che ho messo tutto. So if I compute now the derivative of P with respect to temperature along this line, for which N is equal to NC, I get a 5/2 KB. 5/2 minus 1 is 3/2 again, and therefore we get the lambda again. So I should have a K, so 5/2 KB, and 1 over lambda cubed again, and the G 5/2 of 1. Vediamo se è giusto, 5 mezzi KP, lambda cubo, blah blah. Okay. Now N is equal to NC, and remember that
NC lambda cubed is equal to G 3 half of 1.
Therefore, here I can write
This as 5 half KB divided by lambda cubed.
Okay, G 5 half of 1. And let me put a 1 here in this fashion. Well, I can also derive the lambda cube. Derive the lambda cube from here. This G3 half of 1 divided by NC. Okay. So therefore, this will be 5 half KB G 5 half of 1. And then instead of lambda cubed, I put here G3 half of 1 divided by NC. Okay. So I will write in a better way now in a moment. You see here that some structure similar to this is starting to appear. It's not very evident at the moment, but now I will do it. Vediamo se mi conviene introdurre questo specific volume, maybe sì. So this dt, if I introduce 1 over NC equal to the critical specific volume, this is equal to 5 half KB. Then I have 1 over BC, so BC here. And let me multiply by temperature and divide by temperature for a reason that will be clear in a moment. And then I have 1. Okay. So now if I compare this equation, that's called A and B, which is the Criterion equation, I see that I have a structure like 1 divided by T dt, which is this structure here. Actually, there's no difference in specific volume that I will describe, well, will comment in a moment, but it is a temperature time specific volume. And then what is left is a latent heat, which is in this case 5 half kBT G 5 half of 1 divided by G 3 half of 1. Now this quantity here, let's call it Q, is the latent heat. This was the latent heat for particle, must be, if I'm not mistaken, let me be sure, yeah, I will fix the particle. So latent heat for particle, which is associated with the Bose-Einstein condensation. Okay. 5 half kBT. Yeah. Okay. Okay, so let me make some comments. When we draw the isotherms, we had something like this. where here, if I compare with the van der Waals situation, I have a specific volume here, which is finite, and the other one, which is 0. Whereas in the van der Waals, so this is for BC, for van der Waals, I have these two specific volumes of this potential. So the role played by 1 divided by minus n2, 1 divided by minus n1, here is just played by just one quantity, which is BC, which is the specific volume of the normal phase at the critical point. Okay. The specific volume of the normal phase. N equal to NC, where temperature is fixed. Whereas here, I do not have a specific volume associated with the BC, with the Bose-Einstein, with the condensate, because this is basically 0, if you want. Specific volume of the BC. That's why I do not have here in the structure a difference between two specific volumes, as in this case, because in this case I had a volume occupied by the liquid and a volume occupied by the gas. And here in the Clapeyron equations, it appears the difference between these two specific volumes. Whereas here I have a volume occupied by the normal phase here, whereas a 0 volume occupied by the condensate. And that's why here I just have one volume. Okay, I do not have a difference. Again, this fact is intuitive, but at the same time is a little bit artificial, because here basically I have the particle condensating in a momentum state which is k equals 0, and I can imagine somehow that the volume will not occupy a volume. Actually, this is not completely correct. Well, this is a result of this calculation, and it is correct in this model. In a real situation, actually, the BC is a little bit more complicated. So in real situation, actually particles have a volume, for instance, which is finite. Therefore, I will get volume here actually. And also they interact. So actually, in presence of finite volume, well, or if you want, better to say in presence of interactions between bosons, the BC will occupy a volume. No? And actually, I will comment this later. Actually, it's not even a first order. But it is actually a second order phase transition. And I will comment this later, not today, but next time. Second order phase transition. Okay, so all these features are qualitatively, well, are correct within this model because we are not considering interaction. But in real situation, of course, there is interaction, and this interaction will be important also for the Bose-Einstein condensate because will remove some of these artifacts like case, and not have a finite volume occupied by the particles in the condensate. Okay. Okay, since we have some time left, let's make the next characterization and the last actually. So now we have computed the equation of state. We are making plots of phase diagrams with the PC. Now the other quantity that I would like to compute is the specific heat of this boson gas, in particular close to the critical point for the DC. We will see that there is a discontinuity, not of the specific heat, but of the derivative of the specific heat. And when we have discontinuity, is again a situation that's typical of phase transition. Okay. So now next characterization that we will do of the boson and condensate is the specific heat. Specific heat of bosons. And we will compute it below the critical temperature where we have the condensate, and also above the critical temperature. And we will see that we will discover again the classical limit, but of course we have correction, heavy correction for small temperature, which are also due to the fact that we have a condensate. Well, those bosons are non-interactive. Of course, actually, we will not do any other case, but let me stress that they are not interactive. Okay, the starting point for the specific heat at fixed volume is to make a derivative of the internal energy with respect to temperature by keeping fixed the volume, actually also the number of particles. So this du dt at fixed volume. Now we know that PV is equal, and we prove that the 2/3 of U, which is the classical result, and this is all true also for bosons. And we prove this. The fact that the same relation between PV and internal energy is correct, and holds true also for the bosons. Okay. So now to compute the specific heat, actually we will compute the derivative of the pressure with respect to temperature at fixed volume. Okay. So by using these two equations, the specific heat here, Cv, is equal to 3/2 volume. So 3/2 the volume derivative of P with respect to temperature, fixed volume. Okay. Now let me divide by nkb in order to find the specific volume per number of particles, just to compare with the classical result by nkb, and therefore this Cv divided by nkb is equal to 3/2. When I put here n, I have a density, therefore this is Kb small n, which is the density, and then I have the derivative of P with respect to temperature at fixed volume. Okay, so now we have to consider the situations in which we are at in the condensate, or we are in a normal phase. Okay, so now we have to split.
So for z equal to 1, we know that p lambda cubed divided by kbt is equal to v 5r of 1.
And actually, the derivative of the pressure with respect to the temperature was done before, because in that case,
So this number,
I just need to repeat the calculation that we did before, and the result is the following.
so the cv divided by nkb is equal to, now this for t less than tc,
For t less than tc, I can just repeat the derivative that I did before for the Clapeyron equation,
and I will get 3 half kb n, and the derivative was 5 half kb g 5 half of 1 divided by lambda cubed.
Okay. The only difference here is that I'm not sitting at n equal to nc as in the case of the Clapeyron equation. Okay. And you have that the density can change,
And I have a temperature which is smaller than the physical temperature.
but the result is the same. Okay.
See the diagram equation.
So then for t smaller than tc, the CV divided the specific heat per number of particles and divided also by 2V is equal now to 15.5 kb drops. Cancella. Just one moment. Okay, the 315, and here we have 4. 15 times 4. Then I have g 5 half 1 divided by lambda cube, and then I have a density here. So then I have a density here, lambda cubed, and the g 5 half of 1. That's it. Now, I see from here that the behavior of the specific heat per number of particles in terms of temperature is as a power of t to the 3 halves. Okay? So scales when t is smaller than tc as t to the power of 3 halves. Okay? That of course is different with respect to the classical case, for which the CV divided by nkb is a constant, no? And actually we will recover this constant later, and this is the 3 halves, no? Classical result. The 3 spatial reactions. So instead, here we have the specific heat goes to 0 as t to the power of 3 half. Okay, whereas in the classical case, this is a constant. So this is a first correction, which is of course an important correction. Actually,
you might remember that in the case of photons, you might remember the scaling of the CV with the temperature in the case of photons. Or, well, in the case also of the Bose-Einstein gas that we, sorry, the case of the Einstein model of solids that we commented at some point. No, for massless particles, so for photons, do you remember which is the scaling of specific heat? Okay, for photons. Scales as t to the power of 2. Okay. Whereas for massive particles, as the one, so non-relativistic, as the one we are considering, we have the scaling t to the power of 3. Okay. Now, for t approaching the Tc from the left, I can just use the same formula, and the specific heat divided by NKB is equal to 5 divided by 4, and here you have G5 alpha of 1. And here, if we are sitting exactly at T equal to Tc, and lambda cubed is equal to G3 alpha of 1. Okay. So I have this number here. Therefore, I can make a plot now of the CV divided by NKB. And here we'll have a behavior like t to the power of 3 alpha, then increases and reaches a certain point at t equal to Tc, where I have a finite number, which is this 15 divided by 4, and the ratio between these two numbers. Okay. So the first important point, of course, is that the specific heat per particle, when t is small, approaches 0, is vanishing small, and it goes to the power of t to the power as t to the power of 3 alpha. Okay, so with this quantum correction to the behavior of the specific heat, of course. Now we will see what happens for t larger than Tc. And in particular, we can consider the classical case in which t is very large, and we will see that we will recover the classical limit. And we will see instead what happens when t approaches Tc from above, and we will see that there is a discontinuity of the derivatives, which, when I have discontinuity with some thermodynamical function, is basically a sign of a phase transition. Okay. So now the next step is to compute the specific heat for t larger than Tc. Now this is a little bit tricky, and I will sketch the calculation, but we will finish next time. Because now the pressure, differently from the previous case, it's more complicated because it's kBT divided by lambda cubed, and here you have a G by half of Z instead of 1, because now we are above the critical temperature, and therefore when I compute the derivative of P with respect to temperature, if you want a fixed volume, I get the result, similar result as before, when I'm deriving just this term here. So I have the previous result. So 5 half AB G 5 half of Z divided by lambda cubed. Plus, now I have to derive with respect to temperature also this function here, because Z depends on the temperature. And so I have a kBt divided by lambda cubed. And then I have the derivative with respect to temperature of yeah. Fixed volume, but I can remove this volume now. Because this is a function actually just of z, which in turn is a function of t and b and beta. Okay, so now the thing is to compute this quantity. So the derivative with respect to temperature of the g by half of z. And let's compute this derivative by using the chain rule as follows. Let's make the derivative of z with respect to t, derivative with respect to z of the g by half. Now this is equal, when I'm doing this derivative by using the properties of the Bose function, the derivative of this function is 1 over z times g, this index minus 1. Okay, this is a property that we derived at the beginning. So this is actually 1 divided by z, g3 half of z, and derivative of z with respect to temperature. C properties of G, K, and Z. Is in the definition. It's in the definition. Okay. Now what I need to compute is the derivative of Z with respect to T, and there is a trick that we can make, which is the following. So now the task is to compute 1 over z derivative of z with respect to t, how to compute it. And there is a trick that we can use, which is the following. Let's start with this equation, which is the second equation that we have for a gas, for a quantum gas, which is n lambda cube is equal to g3 half of z. Now let's derive with respect to temperature, with respect to T. And so here I have an n 3 squared and derivative of lambda with respect to T. And here, by using the same relation as before, I can write this as derivative of 1 over z times g 1/2 of z. Okay. So 3n lambda squared, let me check if I have the correct result, is 1 over z, 1 over z, g 1/2, derivative z. Okay, good. Now from here, let me go upstairs. I can see that 1z derivative of z with respect to temperature is equal to n, so 3 n lambda squared divided by g 1/2 of z, and then I have the derivative of lambda with respect to temperature. Quindi 3n lambda square, okay. Now, by considering the definition of lambda is equal to t to the minus 1/2 times a constant, so the derivative of lambda with respect to temperature will be this constant, then I have a minus 1/2, and then I have the temperature to the minus 3 half. Okay. Which is also equal to minus 1/2 lambda divided by t. Minus lambda divided by 2t. Okay. Minus 1/2 is this. Then I have a factor t to the minus 3 half is t to the minus 1/2 times t to the minus 1, and t to the minus 1/2 times k is just lambda. Okay, so therefore you get minus lambda divided by 2t. That we can insert now here. So then I have a 3n divided by g 1/2 of z times lambda squared, 3n lambda squared. Then I have a minus lambda divided by 2t. Okay. Minus lambda divided by 2t. Okay, so we have computed now this quantity from here. Okay. So now let me come back to the previous derivative. We were computing the derivative of pressure with respect to temperature at fixed volume, and there was a first term which was 5/2 kb g 5/2 of z divided by lambda cubed. Then there was plus kbt divided by lambda cubed, kbt divided by the lambda cube, and then there was the derivative of g 5/2 with respect to t, which was 1 over, so g3 half of z, g3 half of z, and then here there was the derivative, so there was 1 over z derivative of z with respect to temperature, which now can be introduced here. So is minus 3 half and g1 half of z minus 3 half and g, then I have a lambda cubed, and then I have 1 over the temperature here. Let's have everything here. Okay, let me check. 5/2 kb, quello lì va bene, kbt lambda cube, g half of z minus 3/2 and lambda cube, g1 half of z and temperature. And let's stop here. It's a little bit heavy. Okay. But okay, the work is finished now. Okay. So we will start from this next time. Andiamo, 1, 2 e 3.
Per quanto riguarda l'esame, metterà delle date fisse o si dovrà organizzare?
No, vabbè, non metto date fisse, poi ci mettiamo d'accordo. Ne farei 5 alla volta. Magari se vi organizzate tra di voi in gruppi da 5. Arrivederci.
Arrivederci.